Notice, and we'll pause it. I want you also to notice, I'll show it again, that it doesn't make a smooth halo. It doesn't make just a big smooth thing. It forms little clumps that move around. So let's take a look again, and I want you to notice this, that at all times in this simulation, you have these little tiny clumps that are always moving in and out. Okay? It never makes just one giant sphere. Okay? Yeah, you get a big central thing in the center. You get a big central thing. But you also have these smaller concentrations that move in and out. And you can see that consistently. So we don't just have a standard halo of dark matter, we have a clumpy one. So we have clumps of dark matter living in our galaxy. And that can provide us with a way to distinguish between different types of dark matter. For instance, dark matter could be these black holes that were formed in the Big Bang of the universe. We call those primordial black holes. And if we have primordial black holes, well, those are just little points that are traveling through the universe, that are traveling through the galaxy. Little tiny black holes that are maybe bigger than Mount Everest, but smaller than the moon. And so that's about how big these black holes could be. Thankfully, we haven't noticed one locating us yet. These could be weakly interactive, massive particles. And if we have these form clumps that aren't points, like black holes are, but these are rather diffuse clumps of dark matter that are maybe a light year or a fraction of a light year in diameter, but only have the mass of about a few Earths in them. And they would be scattered throughout the galaxy. We can also have other types of particles, which I won't go into, but the dark matter you get out of these are somewhere in between this and this. They're smaller than this in size, but bigger than this in size. So they're more dense than WIMPs, but less dense than black holes. And so we have a whole range of things we can look for. And I'd like to know, what can we do with this? Well, one thing I'd like to tell you is we have these near-perfect clocks in our galaxy. So I'll pause this. What a pulsar is, this is a neutron star that's usually formed from a supernova explosion. And this is what's left over often after a supernova, is you have this neutron star that's spinning. But it has a strong magnetic field and an accretion disk around it. And what it does, every time it spins around once, it sends a jet of particles out at you. And it turns out that these pulsars keep time better than anything in the universe except the best atomic clocks on Earth. When I say they keep time better, what we've done is we've observed one of them, a millisecond pulsar, that was found in 1982. And from when it was first found until today, the uncertainty in when any one pulse is going to arrive is about 1 microsecond. So over the span of 25 years, we can measure the accuracy of these clocks to 1 microsecond. That's incredible. That's measuring something to 17 significant figures for those of you who are scientists. That's really an incredible measurement. And so, yeah, I don't think I'm exaggerating to say these are near-perfect clocks. Some of them spin relatively slowly, like this animation here, where you get about 1 blip a second. But others spin even faster, up to about 600 or 700 times a second. So these things are really fast, and they're excellent clocks. But I'm going to tell you what we can use them for. You see, if we have a pulsar spinning around and emitting pulses, and we're over here watching it. Let's say I've got a source right here, okay, sitting around emitting pulses to me. So I'm watching blip, 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 blip. Everything's going fine. What happens if I have a dark matter clump that's way out here and it decides to move this way? Well, when the dark matter clump gets right over here, the light isn't going to go straight to me anymore. It can't do it because space is bent. That's something that matter does. Matter bends space. That's why gravitational lensing works. And that's why the light wouldn't come straight to me. Instead, it would take this bent path. Now, a bent path is longer than a straight line, and so light from a pulsar can only move at the speed of light. So what this means is light is going to take longer to get to me if I have dark matter in between us than if dark matter isn't there. And so this is what I look for. This is what I work on, is saying, well, if we have this dark matter moving through our galaxy, and we have pulsars sitting in our galaxy, and dark matter is moving, can they affect the pulsar timing, which remember is accurate to 1 microsecond over 25 years? Can we use that to detect dark matter and see what type we have, whether we have primordial black holes, or whether we have weakly interacting massive particles, or whether we have axions or something else? So when I do this, when I work this out, we can see that transiting dark matter will change the arrival time of pulses. And I know these pictures aren't as exciting as the earlier ones I've showed you, but this is where I look for my results. And I can see one model will make a signal that looks like this, another model will make a signal that looks like this, and the third model will make a signal that looks like this. Now these aren't very large signals. This is only a few hundred nanoseconds over the span of about 25 years. But can we do this? Do we have the accuracy to do this? Because if we see one of these things, then we know what type of dark matter we have. And if we don't see one of these things, then we can put limits and say, well, if we do have dark matter of this type, it's less than this amount. So what can we say about that? Can we measure a 100 nanosecond difference over a 20-year time span? Okay, so 1 microsecond, that was as good as they could do in 1982. The best pulsar timing data now for the best millisecond pulsar is down to 74 nanoseconds. So yes, yes we can. We can do this. Oh, sorry. 20 years from now. Okay, so just to sum up, I'll tell you, don't be afraid of the dark. Okay, dark matter helps form the universe. It makes this web of structure that we see. It helps us form galaxies and galaxy clusters. We know that it isn't normal matter. We know this isn't protons, neutrons, and electrons because it interacts differently than they do. And finally, we know we can't get rid of it by modifying gravity. Remember, we see these colliding galaxy clusters, and because we see dark matter, we see mass, where there is no normal matter, in all these different configurations, we know that we can't just change the laws of gravity to get out of this. We need dark matter. And we're trying to find it, and we can. We can do this either through experiments or astronomical observations, and we're trying both. So thank you very much.